Hello everyone. Today we will be doing a PSS on number theory. I have mostly selected some problems from IMO Shortlist. So let's get started. And if at any point you have any doubts, then just feel free to interrupt and preferably try to unmute and speak over using chat because that is more convenient for me. So here is the first problem. Okay, so you have a rational number R. R is m over n with m greater than n and m n are positive integers. A rational number R is given, then you have a game on a number line where there is a red bead at, this is not red, but okay, red bead at 0 and a blue bead at 1. And so at in every move, you pick one of the beads. I'll just take green color. You take one of the beads and at any integer k. And then if the chosen bead is at x and the other bead is at y, then you move x to the point so that satisfies x dash. This remains at y, which satisfies this equation. X dash minus x is r to the power k times x minus y. And you have to find all r's is that you can move the red bead from 0 to 1 in at most 20-21 moves. The k that you are choosing on every move can be different. So I hope the question is clear to everybody. I'll give you some time to think. If you get any ideas, just feel free to say it. If you have seen the problem from before and know the solution, then preferably don't spoil it immediately. Okay, does anybody have any ideas?
This would imply that x dash is greater than x.
Yes. So as we have m greater than n, if x is greater than y, then that would imply x prime is more than y. Okay, so let's think about it this way.
No, x dash
We
is greater than x, right? Not y. Because y
oh,
gets cancelled.
okay. Yeah, okay, yes. I thought you meant to say this. Yes, okay. So let's think about it this way. We don't have much control about, firstly, on every move, the integer k that we are choosing is like random. Like there's no condition on it. So we don't have much control over it. And even this equation does not seem like you can really easily factorize it or something. But so what do you think we should try to, like we have to impose some condition on x prime x and so on. So what do you think we should do? We can't get much thing what exactly x prime is and so on. Like k you cannot ignore, k you cannot control, but you have to somehow control this term m over k to the power m over n to the power k. How can you control this term?
Hang on, why can we not control K?
Like k can be anything.
Yeah, which means we can control it. Like we choose K, right?
Yeah, you choose k, but like mm, okay, so are you saying like we should try some construction where you explicitly choose k?
No. I'm just asking what you mean by we can't control K.
Okay, I mean, okay, for example, suppose like r equals something won't work. I'll just say r equals say 5 won't work. Then how do you prove it? For that, you cannot control anything about k, right? In that case, like k is
Okay, yeah.
any random
Like,
number in that. Yeah. So what do you think we should try? We can't focus on k, but we have to somehow focus on this term.
I think like we should use inequalities like to solve the problem, because so like there are so the question says that find all r, so that means that there probably will be more than one r. So and also it is a number theory problem and there are integers involved, so like we can easily single out the answer that we want if we like generate inequalities.
Inequalities, yes, but how exactly will you do them?
Yeah, I need time for that.
Okay, I'll probably write this.
can we like multiply by n to the K?
Sure. Yes, that was what I was going to do. Okay, n to the power this is you get m to the power k x minus y. And another thing I was okay, you have exponent is okay. I'm just rewriting this equation in a different way. Minus y plus minus y times m over n to the power k minus y. And this times x, sorry. And this is m over n to the power k x minus y times m to the power k minus n to the power k. Oh, and GCD mn is 1 because, yeah, we can just choose n to the power k, you have x times. So, can you think of something from your? So, okay, the thing is you have to somehow relate x prime and x. Can you think of anything that you would, that in some information that would relate x prime and x, that would ignore, like that would leave k and that would leave y only in terms of x prime and something in terms of mn? Try to focus on this equation. So basically we want to somehow have to ignore this term. Can you think of a way that you can relate these two terms?
If we never choose the bead at 0, then y will always be 0, right?
Yeah. Yes. So yeah, that is another thing. But the issue with this equation is like you barely can control how things are made. Like, okay, suppose you want to prove, as I said, r equals 5 does not work. Basically, now we are trying to get something which would work and which won't work, because this equation is very weird. So you have to somehow get something better from this equation. Okay,
X
so
prime
for
is an integer only, right?
yes, x prime is an integer. Wait, no, it need not be an integer, because this term need not be an integer. R can be like R is any rational. X prime is a rational. Okay, for any, as I said, we want to relate x prime and x. It's something in terms of r, which is m and n. We want to somehow remove this term. For any y and k, what is common about this term? Wait, I'll probably write it in another way from which you'll see it more clearly. But this m to the power k minus n to the power k times y. Now can you think of something? This is just m to the power k minus n to the power k, n to the power k x minus y.
Oh, wow. Okay.
Like, you could also get this by rearranging it directly, but this is probably what bit more
I
measured.
think it implies that if R works, then R minus 1 would also work. Seems like similar to the question statement.
No, here it is x prime minus y, and the equation we got is x prime minus x. Like, had it been minus y here, then okay, so think about this. What is special about this? This term for any k, what is common about it?
M minus n
divis-
divides it.
Very good. M minus n always divides this term. So now, in the origin in here, I'll just go mod m minus n, and notice m over n is always 1 mod m minus n. And hence, from this equation, you get x prime minus y is congruent to 1 times x minus y mod m minus n. And hence you get x prime is congruent to x mod m minus n. Does that make more sense now?
Yes.
So what this really implies is, okay, we had x comma y, and then we moved to x prime y. Note that they are the same, like x and x prime are same and y prime are same mod m minus n. This is a very important thing because now we have a relation in x prime modulo m minus n. So this was what I was hinting here, like m minus n always divides it, and hence you can, like, if you go mod n minus n, this term just becomes 0. So is this clear to everybody? Why we got this? This is the given equation and event mod m minus n in this equation. So now, what can you say about, so we are starting with the position. So we now know like the thing is going to remain same modulo m minus n, whatever you will do. And you start with red bead at 0 and the blue bead at 1. What is our final position? So, okay, basically this is an invariant in some sense. Which is what I meant by you cannot control K, and hence we have to find something which is preserved. So, invariant. So you're starting with red bead at 0 and the blue bead at 1. And what is the final position? Like, how does the final, where is the final red bead and the final blue bead? The
So
red
like
bead at,
we put x to be like 0 in that equation, so that just gives that x prime is congruent to 0 mod m minus.
yes, but yeah, that is correct. I'm saying the final as in here. Like, what does the problem ask? We want to move the red bead to 1. So what is the final state?
X prime comma 1.
Like the red bead would be at 1 and the blue bead would be at something, right? Like Alice can move the red bead to 1.
Oh, okay, yeah, okay.
Yeah, and as we saw here, under any move, modulo m minus n, like the thing remains same, and hence, after all the moves, the thing would also remain the same, and hence, you get that 1 is congruent to 0 mod m minus n, as you said. What does this imply? This is just, if I write just normal brackets like this, it means what? Yeah, sorry.
It implies that m minus n is equal to 1, I guess.
Yeah, because you get m minus n divides 1, which implies m minus n. Very cool. So what did we prove in all of this? So we started with taking, like, we just inferred that m minus n is 1. And r was m minus n. R was m over n, and hence, if you just see that r minus 1 is m minus n over n, and hence, like, which is what? Basically, m is n plus 1, and hence you get r is this, and hence r is of the form this. Is this clear to everybody? Like if we inferred that r must be of this form. We don't know if this works yet, but we know that it must be of this form if it works.
Makes sense.
Okay, so is this is this part clear to everybody? How we inferred r must be of this form if it works, or should I go over the proof once again?
Could you just go over the proof and say?
Sure. So we had this weird looking expression at the start, and we don't have much control over k, and hence we have to somehow, relate x and x prime in terms of a fixed quantity, which is m and n. So we think about invariants, and we want to somehow get rid of this term. And if you go mod m minus n, then note this term is all. This is always m over n is always 1 mod m minus n. The reason is just multiply m on both sides, and you get m is n mod m minus n, which is true, and from this you go. So this is always 1 mod m minus n, and hence we get x prime minus y is 1 times x minus y mod m minus n, and hence we get x prime is x mod m minus n. And hence, under any move mod m minus n, the position of the beads remain the same. So this is an invariant. You are starting the red bead at 0 and ending the red bead at 1, because that's what the problem asks. But modulo m minus n, the position of the bead remains same, and hence 0 must be 1 mod m minus n, which implies m minus n is 1. And that just gives that r is of the form 1 plus 1 over n. Is this clear to everybody? I hope so. But
Okay, where did you use the fact like at most 2021 moves?
Yes, that is the thing that I said. We said that if r works, then r must be of this form, 1 plus 1 over n. But we don't know if 1 plus 1 over n would work, right? And
okay,
so for which end does 1 plus 1 over n work? That is when we will be using this at most 2021 moves. So let us try basic base cases. First case is n is 1, in which case r is, okay, I'll just directly write the value. Okay, never mind. N is 1, r is 2. So I'll let you try this. Now have x prime minus y is 2 to the power k times x minus y. So at the start, you have, like, we are just now trying out stuff and trying to guess this, see the pattern, okay? So at the start, you have red bead is at 0 and blue bead is at 1, and we want to move the red bead from 0 to 1. So let's just start by trying to move the red bead. So initially it is at 0, blue bead is at 1, and you get x dash minus 1 is 2 to the power k. This is like on the first term. Hence you get x dash is and we are going to negative, so we reject this idea. First, let us move the blue bed. It is at 1, 0. It is x dash minus 0 is 2 to the power k. And hence you get x dash is 2 to the power k. So now you initially had 0, 1. You can now move it to 0, 2 to the power k. Now let us try to move the blue bit. You have x prime minus y is this equation. Now we are going to move the red bit, and hence x prime, y is the blue bit, which is at 2 to the power k, is 2 to the power, I'll take different k, which is L, times 0 minus 2 to the power k. And hence you get x prime is 2 to the power 2 minus 2 to the power k plus L. Do you see how we can make x prime equals 1? We can just pick any KL so that x prime would be equal to 1. Can you come up with any construction?
Wait, L can be negative also.
Yeah, the k, like in the problem it says k is an integer. So you are free to
Yeah,
take
so we
any
can
integer.
just have 2 to the 1 and 2 to the 0.
Very nice. You can take
So
k
1 and
equals
minus
1
1.
and L is minus 1. And hence we reach x prime is 1. Is this clear to everybody? So we know that r equals 2 works because we reached it in 2 moves. R equals, wait, n equals 1. We reached in 2 moves. And you cannot reach in 1 move because, as you saw earlier, with editing. So I hope this is clear to everybody. And now let us try for n equals 2. You now have r is 3 over 2. You have x prime minus y is 3 over 2 to the power k times x minus 8. I'll probably pick a different color this time. So I think when I was saying during the first move, we are trying to move the red, we are trying to move the blue bid. If we try to move the red bid, I think I said we get negative, which is wrong, but we'll see later. Okay, so here again, let us try to move the blue bid. You have x prime minus 0 is 3 over 2 to the power k times 1 minus 0. And hence you get x prime is 3 over 2 to the power k after one move. After second move, now let us try to move the red bead. And what do you get? You get x prime minus 3 over 2 to the power k is 3 over 2 to the power L times 0 minus 3 over 2 to the power L. Hence you get x prime is 3 over 2 to the power 8 times 5 minus 3 over 2 to the power. And we can't really win in two moves anymore. We have to proceed. Let us go to the third move. And you get x prime minus y is, wait. So, okay, what do you think we should move now? The red bead or the blue bead? Probably it does not make much sense because it seems random at this point, but why would you move to, why would you try to just move the red bead 2 times? You could have just moved it once maybe. I don't know. Okay, so you just have actually move the blue bid now. We first move the blue bid and then the red, now blue. I give it because you just have to work out on your own and then maybe see. And after the third move, you'll get x prime is x prime minus the which is at 3 over 2 to the power k times 1 minus 3 over 2 to the power l is 3 over 2 to the power n times, this is at 3 over 2 to the power k minus this thing. Which gives x prime is 3 over 2 to the power n times 3 over 2 to the power k plus n, and it is already getting weird, plus 3 over 2 to the power k times 1 minus 3 over 2 to the power n. And as you can see, terms are getting weird. So why don't we just pick some basic values for k and n? What did we pick for the first turn? What did we pick last time? like it is getting messy. We just have to keep it little easy. So let us try our luck and hope that basic like small values would just work out. What do you think we should pick, K? What did we pick last time?
Can you scroll up a little?
Sure. So just let
Okay,
us
so I
try our
was
luck.
thinking about
Yeah.
like I was trying a different approach because
Mm-hmm.
but I'm stuck like at a point. So it it is given that like we have reached the point where r is n plus 1 by n, right?
Yes.
So what if we like put this in the equation that was given to us,
Mm-hmm.
and so we get that n to the power k times x dash minus y
Mm-hmm.
is equal to n plus 1 to the power k times x minus y.
Okay.
Now, as we considered mod m minus n, like now the equation is completely in terms of n.
Yeah.
And also, if we like add n and n plus 1, we get 2n plus 1, right?
Yes.
So if we consider mod 2n plus 1,
Okay.
we get that n. So obviously n to the power k will become 1 to the power k, like considering the congruency, and n plus 1 to the power k will become minus 1.
Yes.
So like we can get two equations based on whether k is even or odd.
That is extremely nice. I was first doing some basic examples, and that is extremely nice. So what Rishad said is go, I'll probably write it down here. You have to go mod m plus n this time, which is just 2n plus 1. But you have m over n to the power k. Last time we went modulo m minus n, and we got this is always 1. What will happen if we go mod m plus n? Note m is like negative n mod m plus n, and hence m over n is congruent to negative 1 mod m plus n, which is nice because we have a minus 1, and hence m over n to the power k is congruent to negative 1 to the power k mod m plus n. I'll just write this as plus minus 1. It can be 1 or minus 1. And hence what do we get? We have x prime minus x is m over n to the power k times x minus y. Wait, x minus y. Yeah. Go mod, we are going mod m plus n, and we get x prime minus y is negative 1 to the power k x minus y. I'll just write this as plus minus 1. If it is plus 1, we get x prime is congruent to y, x prime is congruent to x mod m plus n. And if it is minus 1, we get x prime minus y is congruent to minus x plus y mod m plus
No,
n.
it is minus x minus y.
Oh, sorry, my bad. Thanks. And if you just rewrite this, you get x prime plus x over 2 is y mod m plus n. M plus n is 2n plus n, which is 1. So now we have, after every move, modulo m plus n, you have x prime comma x is like either x comma y or x prime plus x is over 2 is y. And this is certainly useful.
So y becomes the arithmetic mean of x and x prime. So it lies exactly in the middle.
Yeah, but the issue is this equation is mod m plus n. It is not equality.
Oh, okay, yeah.
Yeah. So again, we just have modular, modular information. We don't have anything about the numbers, which is why we were trying to, construct this and see if there's any pattern. Remember, the question says at most 2021 moves. So there probably would be some significance of that. So let's just take k. We're going back to r n equals to 2, r equals to 2. We take k equals 1, and let us just take l is minus 1, and you get initially you are at 0 1, then you go to 0 comma 3 over 2, then you will go to minus 1 to 1 minus 2 over 3, 1 over 3, you get to 1 over 2 comma 3 over 2. Again, let us just pick. Here we are going to pick, this is n is 1, and you will see that we will go to half comma and like we moved on blue bead, then red, blue, and now we again move on the red bead and pick minus 1, I think, again, and you get to 1 comma 3. Okay. I might have messed up something here. Like I might have messed up the value of this, I think, but that doesn't really matter much. But just by picking 1 minus 1, like just pick nice numbers. And luckily in this time, we are also, for n equals to 2, we are reaching in 4 moves. So somehow keep this in mind, and we will now go back to this. So just a second. We now have to use this condition. We have to somehow bound the number of moves. Like from 0 comma 1, you have to go to 1 comma something in at most 2021 at most 2021 moves. You have to somehow bound the number of moves in which you are, like you have a bound on how many moves you're going. So you have to try using this and getting something. So yeah, as we have here, if you go mod 2n plus 1, every move essentially like this does nothing, or you go to the arithmetic key. So you are starting with 0 comma 1. This is the start. From this, where can you go? Both arrows, as in we can go from here to here. If you do like any move, what position will you get? Suppose we are going to fix the blue bit now. You get 1, and what will happen to the red bead? Where would it go modulo n plus n, which is just 2n plus 1? What would the position be? This would be 2, right? Because like from this you can either go to, if you have either this case or this case. Note we are working in mod n plus n. So from here we can either go to 0 comma 1, but we are trying to consider new places that we are visiting, and or either you go to something that satisfies this. So you have x prime x prime plus 0 over 2 is congruent to 1, and then you get x prime is 2. I'm not saying position this, I'm just saying modulo m plus n you reach here. So what if you move on this again? Okay, now this time if you fix the blue bit again, you will go to something comma 1, note this would be 0 comma 1, right? But we have already visited this. We are trying to see which new places we can reach. So this time we fix the red bit, and from 2 comma 1 where can we go? 2 comma what? Suppose we go to some x prime, then we must have that x prime plus 1 over 2 is like we can either go here or here, but in this case it's like from 2 comma 1 we are going to 2 comma 1. There's like nothing new modulo m plus n. So we are just trying to see what are we are reaching. X prime plus 1 over 2, this is like 2. So what is x prime?
Three.
Can you just repeat what you said?
Like right now using
What
this
did you say, like
information-
after 2 comma 1?
After 2 comma 1, okay. Firstly, keep in mind that we are going to go to new places. We are not trying to repeat places. So we are essentially rejecting this idea as of now. If you fix blue bit, which is 1, then you will go to x prime comma 1. But note that x prime would just be equal to 0. Or you can fix the 2. In which case we'll go to 2 comma x prime, which is this position. Did that make sense? We are not going here because in this case
yeah.
we reach 0 comma 1, which we have already reached. Like this is nothing formal. We are just trying to explore. And yes, we go to x prime would be 3. So we go to 2 comma 3. Again, on the next move, where do you think we can go? Like a new position. Now we will be fixing blue, because if we fix red, we will go back to 2 comma 1. Now we will be fixing blue, something comma 3. We must have x prime plus 2 over 2 is 3. What would x prime be?
4.
Yes, so we go to...
Yeah.
And do you notice any pattern?
You're reflecting each time. You reflect the y bit in the x bit or the x bit in the y bit.
Yes. Yes, but this thing just, if we just keep following this,
Also,
after
I
this
don't know
we
the problem. So what do you want to reach eventually?
you have to reach wait, I'll just quickly show it. You have to reach from 0 comma 1 to 1 comma something in at most 20-21 moves.
Find all r from... okay. And like you're doing something modulo m plus n. So is it like reach
Yes.
some 1 comma modulo n plus n in those many moves?
Exactly. So here we are like after one move we can so then we will go to 6 comma 5 and so on. And here we fixed blue. Instead of this, if we fix red, like in the other direction, you go to 0 comma x prime, then you'll get x prime plus 1 over 2 is 0, and hence x prime is minus 1. Minus 1. And similar to this side, you can this you get minus 2 comma minus 1. Then
minus
you
2 comma minus 3.
minus 2 comma minus 3 and so on. This is some weird, but you see it in this direction. So
No, these two things always differ by 1, the two coordinates. So if you want to reach, say, you want to reach 1, n, then n should be either 0 or 2.
Yes. Yeah, but like what you
How do you
said
know
before works. What you said before, I was just trying to extend it on the other side. And notice it on either sides, like you just have this sort of pattern, and you want to reach. Okay, notice this things is always like being even. So like even as in the numbers look even now. You want to reach 1 mod 2n plus 1. What is the smallest number you think you can reach if you just go 2, 4, 5? Sorry, 2, 4, 6, and so
2n
on.
plus 2.
Yes, 2n plus 2. Because 2n plus 2 is like 1 mod 2n plus. We are taking 1 mod this because we have to make this 0 reach 1. And 1 is 2n plus 2 mod 2n plus 1, which is even, like looks even. And when do you think we can reach 2n plus 2? We can't reach it in one move, obviously, because we saw from 0 you can go to either 2 or remain at 0. See, in one move, like, okay, you have to reach 2, you have to take at least one move. If you have to reach 4, you have to take at least 3 moves. If you have to reach 6, you have to take at least 5 moves.
Yeah, so 2n plus 2 takes 2n plus 1 moves.
Yes, so you have to reach 2n plus 2, we'll have to take at least 2n plus 1 moves. Right? Even if you go on the other side, it's just the same thing. So you have to reach 2n plus 2. It will take at least 2n plus 1 moves. And note we have 21 moves, and hence you have this bound n is at most 1010. Like 2021
Yeah.
is at most 20,000 moves. If 2n plus 1 is more than 2021, then you can never reach 2n plus 2 in 2021 moves. Because in order to reach 2n plus 2, you need to take at least 2n plus 1 moves. Is this clear to everybody? Why we need n is at most 1010.
Yes.
Okay, cool. Others?
I think so.
Very cool. And construction, I'll just leave. It's you essentially do this thing on this side. And from 0, 1, you can go to, you just pick 1 minus 1. Like we were picking k equals 1, l equals minus 1. You just pick 1 minus 1, like I don't remember exacting, but from here you can go to, I think, 0, 1 plus 1 over n. Then you go to 1 over n, 1 plus 1 over n. Then you go to 1 over n, 1 plus 2 over n. And then you go to 2 over n, 1 plus 2 over n, and so on. And you will reach 1 in, like, this would be 2n or 2n plus 1, whatever. These many moves. So is the proof clear to everybody? We got R must be of this is the construction. Okay. R is 1 over n for n is at most 1010. We proved this works, and we showed that these are the only things that can work. If there's any doubt, just feel free to. You take case plus minus 1, alternate it, and we'll reach 1, yeah. Okay, if there are no doubts, then I'll move on.
I have a question.
Yeah, go ahead.
How can you show that you can't get it faster if you move R 2 times or something?
Okay, so note we can reach 2, 1 in at least one. Like if you have to reach 2, 1, you'll have to take at least one move. right?
Yeah.
If you have to reach 4,3, you'll have to take at least 3 moves.
How can you show that you can't do it faster if you're
Yeah,
moving
yeah, yeah.
something? I
Because
don't know.
if you go from here, the only position you can go to is this, or 0, 1. Like from this position, you can either go the next move you would be at 0, -1, 2, 1, or wait, I'll write it here. That will make it better. You can go to 0, -1, 0, 1, or 2, 1. But here you just started back where you came from, so this would obviously take more steps. Right now we are focusing on this thing. From here you're going to the other side. So from 2, 1, you can either go to 0, 1, or remain same, or go to 2, 3. You can just
Okay.
check this way.
Okay.
Here you came back where you started, so that is like useless. Here you remain same, useless. So this.
Okay, got it.
So that to reach 2n, you take like at least 2n or 2n plus 1 step, whatever that thing is. Okay, so let's move on. Next problem. So you have A is wait, I'll stick with blue. A is given, and then B is good if an plus 1 divides an choose B minus 1 for all n with an greater or equal B. You have B is good, B plus 2 is bad, prove that B plus 1 prime. I'll just rewrite this. You have this condition is an plus 1 times b factorial divides an minus 1 all up to an minus b plus 1. Yeah, plus 1 minus 1.
Shouldn't it be minus b factorial because you're multiplying both sides by b
Oh,
factorial?
sorry. Thanks. My bad. Yeah, minus b factorial. And let's just call this weird looking term. Like weird as in long term, just and this is true for all n.
Can you show the question again?
Yeah, sure. Yes.
Can we use polynomials here? So like set an to be x, then the right hand side. So basically, if we just consider the m term, it will have like 0, 1, and b minus 1 up to b minus 1. So all these b will be the roots of the polynomial.
Uh,
And if
okay. Yes. But the issue is, in that case, like this, just it becomes a polynomial, and you have to focus on en. You have to focus on this a2. Like this is only more seen as in a divisibility equation rather than a polynomial. Okay, we sadly don't have a lot of time. Okay, so in general divisibility, you have something divide something, where this is like a variable thing. So what is the most common idea? Like you have something divide something, you just take prime divisors, right? Because primes are easier to work. So we take a prime p dividing what?
an plus 1.
Yes, you take p divides an plus 1. P divides an plus 1, and p is a prime number. When can you do so? Like for all n, we are going to pick some n. When can you do so? Like what would be the condition? P does not
Can't we
divide.
like always pick n if like
No. P does not divide A. P divides A, you cannot pick.
oh right.
So what do you get from here? You get that P divides this, and hence P will divide an minus 1, all up to an minus b plus 1 minus b factorial. So we would be happy if P ended up dividing this thingy, right? Like this looks weird now, but if P divides this, then it would be nice. So
Yeah.
when can P divide this? Like P divides an plus 1. The term just before this would be P divide, like the number just before an plus 1 divisible by P would be an plus 1 minus P. And this would be divisible by P if and only if an plus 1 minus P is there in the sequence, which can happen only when B is at most P. So if B is at most P, then if B is at most P, then you get P divides B factorial. Wait, what? I think I have messed up something. Oh yeah, you need the other side. Sorry, my bad. Yeah. That makes sense. So if you have this, then you get, if I do this, B is at P, then we know P divides M. But if you put it back, then we know, then from this we'll get that P divides B factorial, which is anyways true because B is greater or equal to. So we don't have we directly don't get some information, but we can try to do something stronger than this. So now we will drive our attention, let P be a prime and B at most P. Sorry. Yeah, B is at least P. We just got a thing that we already have. How do you think we can strengthen it? Okay, in this case, you just get P divides M. But what if we take something stronger than P? What can we do instead of P? And we have to also use this thing. Yeah, it's an plus 1 times B factorial and not just P. What if we take like P to the power, N? N is not used, right? Yeah. Let P to the power N divide. I sadly don't have much time. I have to. Wait, is my screen share? Yeah. I sadly don't have much time. I'll have to give the idea. But now we are just going to work P divides this both of the sides. So we know, call this side left hand side, like this is the right hand, like left hand side and right hand side. We know that VP of the left hand side should be at most VP of the right hand side. So if we somehow make bound, like if we somehow bound VP of RHS, then that would be nice by picking some N. Okay, what is the VP of LHS? We know the VP of LHS is at least VP of AN plus 1 plus VP of B factorial, right? Ignore this for now. I'll come to this later. And we know that P divides AN plus 1 because we have taken so. And hence we get 1 plus VP B factorial is at least this. Is this clear to everybody? We know that VP of LHS is equal to VP of AN plus 1 plus VP of B factorial because it's just the product. And we know that VP of AN plus 1 is at least 1 because we have taken P divides AN plus 1. And hence we get 1 plus VP B factorial is at most VP of RHS. RHS is M minus B factorial. So when do you think we can, forcefully force a contradiction to this equation? Like, okay, this holds. Oh, what do I need to wait? Okay, so we have this thing for all P, for all N, so that P divides N plus 1, P prime and P at most P, okay? So what do you think is the most reasonable way to somehow force some weird contradiction? Because we have taken two assumptions here. These are our two assumptions. The real way to motivate is you take P at most B, because in that case, you know that P would divide both of these and things look better. We can now take a higher prime that divides both of the sides, like P to the power higher N divides AN plus 1 and so on. And hence we, take this thing B. And in that case, we get this. So what do you think is a very reasonable way to force a contradiction? What will happen if VP of M is like is, huge. VPM is huge. In that case, what will VP of M minus B factorial be? We know this has huge VP, and we know this has bounded VP. So what is the VP of this term? It's VP of B factorial, right? Because this has a huge VP and this has a bounded VP. Like VP of A minus B is VPB if VP A is more than VPB. This is true in general. So if we force this, if I'm saying if we take this, then we will get 1 plus from this equation, we will get 1 plus VPB factorial is at most VPB factorial, which is a contradiction. And hence, if we somehow end up being successful here, we would be done. We would like get a contradiction, not done. Okay, that probably might have not made much sense, but
Can we like choose a value for B?
choose a value for
B.
no, B is like they're saying B is given in some sense. N is what we are going to pick. So now let us just try to focus. So right now our goal is to make VP of M huge. I'll explain again later why we would get a contradiction from here. So now we know that AN, I think I'll erase this, but we know that AN plus 1 minus P is divides M because of this assumption. We want to make VP of M huge. What do you think is, and now how do you see how we can construct this? Like how can we ensure this?
We take it like some exponent of P.
Yes, yeah, I'll just call this N for now, capital N. Note capital N and small n are different. And how can we ensure P to the power N divides M? How can we ensure that? Remember, we have this. This is because we have taken B's at most P, so this is this, and we know P divides this. So what if we take P to the power N divides AN plus 1 minus P? Firstly, see why we can see how, what would this infer? This would infer that P to the power N divides M, right? Because of this. This equation holds because P is at most P.
Okay.
Yes, and secondly, let us see why we can pick such a N. Okay, so we have picking an N. That is always that stressed, but we can pick this because this is equivalent to remember P does not divide A, the condition, and this is equivalent to N being P minus 1 over A mod P to the power N, and you can do this because A is co-prime to P. So you can just pick such an N. So now we took, I'll explain again. We took P divides AN plus 1. This would need P at most, P does not divide A. And this just gave us the fact that P divides, an minus 1 all up to an minus b plus 1 minus b factorial. And if b is at least p, then note an plus 1 minus p is at most an plus minus b plus 1, just because b is at least p. And hence, among this term, capital M, there would be this term an plus 1 minus p somewhere, right? Because it's product of b things, and like this term is there in between the extremes. So we get that an plus 1 minus p divides M. We took, this is like our assumption, we took p to the power n divide where n is huge. You can just pick any large enough n, huge as in it's large enough. P to the power n divides an plus 1 minus p, which divides m. This is what we took. You can always take this, like you can take for some n. This would imply p to the power n divides m. And now go back to this equation that we have. I'll just call this equation something star. The star equation says that an plus 1 times b factorial divides m minus b factorial. And now compare VP on both sides. VP of an plus 1 times b factorial is VP of an plus 1 plus VP of b factorial, which is at least 1 plus VP b factorial, because p divides an plus 1. And VP of m minus b factorial is VP b factorial. The reason is VP of m is huge. Huge. So VP of m is, in fact, you can just pick any n so that VP of m is more than VP b factorial, and this would imply this. And now notice what we have got. The left-hand side has VP. The left-hand side has VP this 1 plus at least this. This is VP at least 1 plus VP b factorial, and this is VP exactly equal to VP b factorial. Do you see why this is a contradiction? This side has more VP than this, and this divides it. Should I explain it once more?
Just scroll it up a little.
Sure. Yeah, this is like, this is the thing. I don't think there are explanations from here, nothing before this. But do you people see why this is a contradiction?
Yeah.
Very nice. And why did we get a contradiction? Our assumption must have been wrong. What was our assumption?
B is greater or equal P.
Very nice. So this was our assumption. And the motivation to take this was if like B is not, at least like if B is smaller than P, then P does not divide any of these terms. So we don't really have, like, we don't have some nice information about, like, we can't, this is our star equation. We can't really enforce some nice information from star equation. So that was our idea. So what did we prove? We took P any prime, provided P does not divide A, pick some n so that all of the stuff. If p divides an plus 1 and p to the power huge divides it, everything. And we took and we assumed b is at least p, and we got a contradiction. So what was our, and hence this assumption is wrong, and hence if p divides a, p does not divide a, that implies b is smaller than b, which means that all prime, hence all primes at most b dividing. Is this clear? Because if p is a prime at most p, then for this to hold, like if p does not divide it, then we would get a contradiction. So p must divide it. This just implies this. Or is there any part I should go over once again? Like if p is at most p, then if p does not divide it, then this would imply b is less than p, not possible because we took this. Therefore, p divides it. Okay, I'll take that as a yes. And we now have this very important equation, very important thing, that all primes at most be divided. And this is a lot of information. Let us just go back and notice the equation that we had. An plus 1 times b factorial divides an minus 1 all up to an minus b plus 1 minus b factorial. And like essentially in some sense we are trying to characterize b, because we know a is given and we have some very good condition about b. We are just left to do some very small work. What is the GCD of these two terms? I'm just sadly have to give the ideas because we don't have much time. What would the GCD of these two terms be?
1.
Yes, because if p divides an plus 1 and p divides b factorial, this would imply p at most b. This would imply from here p divides a, and this would give a contradiction. So GCD is 1, and this now holds if and only if an plus 1 divides this called term m minus b factorial, and b factorial divides m minus b factorial. Because the GCD is 1, and then you can separate the things. Now, why is do you see why this is equivalent to b factorial dividing m? But do you see why this is obvious? Because this is product of b terms, b consecutive terms.
Yeah, makes sense.
Yeah, so it's product of b consecutive terms, and then this would always be true. So now we are left with this. An plus 1 divides this. Divides an minus 1, an minus b plus 1 minus b factorial. And can you simplify this equation quickly? Like quickly as in something easy-ish, easy idea. We don't have to take like a prime dividing and then. What is this term? Yeah. It's just minus 1, right? En is minus 1 mod en plus 1, right?
Yeah.
Yes, this is what is en plus 1?
-2.
Yeah, and this is minus b. And hence this is an plus 1 divides -1 to the power b factorial minus b factorial. -1 -2 all up to minus b multiplied to get this. So what does this imply?
So either like an plus 1 divides like 0 or an plus 1 divides 2b factorial.
Yeah, you get an plus. No, that is like, oh, not entirely true, but you can you get -1 to the power b minus 1 and pick. Note that the GCD of these two things is 1. Right? This is because this is what we did here. The GCD is 1. And hence you can remove this factor. And hence you get an plus 1 divides -1 to the power b minus 1. What does this imply? For all n.
B is even.
Yes, be even. Very nice. So we inferred that all primes, hence this like B is good implies all primes at most B divide A and be even. And if you have these two things, all primes at most B divide A and be even, you can just backtrack this thing. Like I'll just quickly summarize it. An plus 1 and b factorial would again be co-prime because all primes at most B divide A. And hence this equation holds if and only if, like this equation would hold if you have these two things divisibilities. This equation always holds, and this equation holds if and only if this holds, if and only if this holds, if and only if this holds, and this holds when b is even because you just get 0 here. So this equation holds and this equation holds, and hence this also holds. What we actually did is this is an if and only if condition. Like I did not explain it properly. You can just maybe see it later that from this how we implied this, it's just the exact background. Because the GCD is 1 and hence this is just if and only if. So did that make sense?
Yeah.
Very nice. So we now prove that B is good if and only if all primes at most B divide A and B is even. Which is very good. We have characterized B, right? Now go to the problem and it says B is good and B plus 2 is good. Prove
B
that
plus
B
2 is
plus
not
1
good, right?
Sorry, my bad. Right. Thank you. B plus 2 is bad. Prove that B plus 1 is prime. I'll let you finish this because I find this finish really funny.
So is it like there needs to be a prime between B and B plus 2?
Exactly. It's because this implies this be even and all primes at most B divide A. Because of this if and only if, note that B plus 2 is also even because B is even. And because of this if and only if, this is where we use the if and only if condition. This must imply that all primes at most B plus 2 divide A doesn't hold. Because if this holds, we anyways have b plus 2 even because b is even. Like if this would have hold, you get all primes at most b plus 2 divide a and b plus 2 is even. And hence by this direction, you get b plus 2 is good, contradiction to what we are given. So this statement does not hold. Now you have all primes at most b divide a and all primes at like there is some prime at most b plus 2 which does not divide a. And this prime must lie between b and b plus 2. And as b plus 2 is even, like the prime cannot be b plus 2, and hence the prime must be b plus 1. The prime as in the prime for which this does not hold. So is the finish clear?
Yeah.
Very nice. And are there any other doubts in the proof? I think I went quite fast in this. Should I explain how I got this? Especially the
Can
first
you
one,
like
because-
send the screenshot something?
Yeah, sure. I can
Discord.
send the PDF on Discord. Okay, so if there are no doubts, then I'll stop.
Also, can you suggest some reading for like VP? Like
Yeah. So Modern Olympiad number theory by Aditya Kutni is really good book. I
Okay.
like it a lot, and that is from what I mean. Okay, so I think I'll stop.